They are the attraction between atoms, ions, or molecules that hold them together. There's 6 different types of IMFs. Okay, and they explain why different things are different states of matter. To determine the type of IMF we'll exhibit, you have to look at the types of atoms that are present in the sample and identify those atoms as either metal or non-metal. So that's your first step. Just keeping up with your, okay, good. All right, so here is kind of a chart of these from weakest to strongest. Now, the issue with this is sometimes your London dispersion forces will be stronger than a dipole-dipole. So when you're comparing like things, for example, if I had 2 iodine, okay, 2 iodine, those are nonpolar. All they're going to have is LDF. But we know iodine is what state at room temperature? Solid. Look at the periodic table up here. Do you see if it's in black? If the symbol's in black, that means that it's a solid at room temperature.
Oh, okay? Dang. So true.
If it's blue,
it's a liquid.
Then it's a liquid, and if it's green, it's a gas.
So what is good for bromine?
Okay. So we know that only has London dispersion forces, but yet it's a solid at room temperature, as opposed to water, which has London dispersion, dipole-dipole, and hydrogen bonding, and at room temperature it is liquid. Okay? So that means that the London dispersion forces are going to be stronger than all 3 of these combined in the water. Okay, so be careful with that when it comes to IMFs. Sometimes just having this, especially when you have...
Bella. Jordan, that is very interruptive.
Yeah, we were focused.
That's the goal.
Okay. Bye. I got my
Bye.
Is it from Bella?
Bye. Yeah, buy a bottle.
I bought it for myself.
Good job. Okay, why is...
So we're going to talk about why that is. I'm just giving you kind of a rundown of what these look like, okay? So the first one is London dispersion forces. Then we have dipole-dipole. Then we have a special form of dipole-dipole called hydrogen bonding. We have ionic, we have metallic, and then we have covalent network, okay? And that's kind of, if everything's equal, these are going to be the strongest, okay? That's why diamond, you can't, cut it. It's really hard to try to change it. All right. First type exists in non-metals only. These are called London dispersion forces, okay? These are caused by atoms, molecules, they naturally have electrons that are moving, okay? And sometimes those electrons end up on one side or the other, okay? Just kind of a natural state. Go ahead.
Just
That's fine.
quick, sorry. I don't know if that took care of it or not. Yep, now you got an address again, but I need to
Okay, can you turn the Wi-Fi off then and let me connect that way? Because then...
Yes, but if it
goes out, go back to the Wi-Fi.
And then it can connect to BYOD. So.
Okay. Yep.
Same MAC address. Okay. All right. What were you on? Input here?
Yep.
Right there.
Yep.
There
Perfect.
you go.
Thank you so much.
You bet.
Okay, so these electrons are naturally moving around, okay? They bunch up on one side. That means that one side is going to have what? Charge. Negative. Now, that is then going to induce the other side to go positive, okay? And shift the electrons over here. It's called an induced dipole, but it's very short-lived, okay? So because of that, if we have atom or molecules of similar numbers of electrons, and one has dipole and the other one only has LDF, then that means that the LDF is not going to be as strong as the dipole. Okay. Now, as you increase the number of electrons, the LDFs increase because you've got more electrons shifting around. I talked to you guys last year, the year before, my kind of analogy with this one is if I have a cup of water and I'm walking across the floor, it's probably not going to slosh out. But if I have a big tub of water that's almost full and I walk across the floor, you know how you get that sloshy, and eventually it's going to be sloshing out. Okay? No. Well, actually, one of your labs you kind of do that with, but anyway, as you're doing that, the same idea holds true with the electrons. You got more electrons to shift, the stronger this force is going to be, and that's why when we go down, remember fluorine, okay? Fluorine bonded with a fluorine is going to be a gas. Chlorine bonded with another chlorine is going to be a gas. Bromine bonded with another bromine, liquid.
Okay.
And iodine is going to be a solid because they've got more electrons.
LDFs get stronger as you go down.
Well, as you go even across the group, they're going to get stronger because, well, as you go down, because you're not going to, they're only in non-metals, so yeah.
So like distance from the nucleus, like.
Well, no, it's number of electrons.
Okay, so like
because the electrons become more polarizable.
Okay.
The more electrons you have, the more polarizable that molecule becomes.
So like how big the radius does not matter.
No, because it's the number of electrons. It's the number of electrons that make the difference. You get more electrons, your LDFs are going to go up. Okay? Make sense?
And when are they stronger than dipole?
When you've got so many electrons that they kind of outweigh or it outshines the dipole and the hydrogen bonding. Okay? Everything has LDF. So when they ask you to list the IMFs present, write down LDF. Just start there. Yeah, but most of our molecules are nonmetals. So, it's a molecule. So most of the covalent stuff is going to be a nonmetal. Okay?
You got more?
Yes, I need my video interrupted a couple more times.
Can you catch it or not?
No, I don't want that one. That one's bad.
Oh, Ray,
What one do you want?
Ray, you're paying for this.
Okay. That was another green one. Hey. Bye-bye. Are you sure that's it, Jordan? Sorry to interrupt you.
I might be back, but
No.
All right.
Here we go.
This one says the wrong green number.
Okay, so the ability of an atom to form a temporary dipole is called polarizability. Okay, so they are more polarizable. They love this term. They love it when you use this term. Okay, this is if I have a highlighter out, I'm going to highlight this term because, yeah, they love it. Okay, so London dispersion forces are stronger when an atom or molecule has more electrons. This is shown, like I said, in the halogens. You can see that going from them being liquids, gases, down to liquids and solids. They increase in LDF due to the increase in those electrons, which makes them more polarizable. They love that term. Okay. Another factor that increases the LDF is the shape of the molecule. Long, thin molecules have more surface area, so they are more polarizable. Round molecules have less and are less polarizable. Also enhanced by pi bonding, the presence of a double or triple bond. All right, dipole. When you have a polar molecule, we talked about molecules being polar or nonpolar. These are permanent dipoles. Okay, one end of the molecule is going to be negative, one end is going to be positive. So that will attract the other side here, another molecule of the opposite charge side. These then also have what? If it's a dipole, it also has LDF. Okay. So when they ask you to list all of the IMFs, you start with LDF, and in this case, you would add dipole. Dipole, then, our interactions are stronger when the substance involved is more polar. The more polar it is, the more or the stronger the IMFs are going to be.
LDF is an accepted abbreviation.
Yes, LDF is an accepted abbreviation on the AP exam. IMF, which is intermolecular forces, is also an acceptable abbreviation. Don't waste your time. Yep.
Is ZEFF also accepted?
Mm-hmm. I don't know if there's an abbreviation for hydrogen bonding. You could do H bonding, H dash bonding, because hydrogen's abbreviated H. I would say dipole.
I would too.
I don't know if that's accepted or not, and so I wouldn't take the chance.
So if it's polar, it always has that.
Yep, if it's polar, it's always going to have dipole.
Can it have dipole and non-polar?
No.
No, because it's only when you have a positive and negative end.
Positive and negative pole. Dipole.
Okay, hydrogen bonding then. Hydrogen bonding is kind of a confusing term, okay? Honestly, if most chem teachers could go back and rename it, if we could build a time machine and go back, we would have them name it something else. Because a lot of people think that because it's a hydrogen bonded to something else, that is hydrogen bonding. That is not hydrogen bonding. No, not very long.
What was this phone?
Yes, this is foam. Okay. So, guys, you two, stop it. It's going to occur in molecules that have an HN, HO, or HF bond. So, it's going to happen here because, remember phone. It's on the phone, F-O-N. Okay.
I'm having fun with hydrogen bond.
Yes, I'm not having fun with you talking all the time, though. The reason why this happens is because oxygen, fluorine, and nitrogen are very electronegative, meaning they are going to hog the electron from the hydrogen, and it's going to cause this to be more negative compared to the hydrogen here. When that happens with another molecule, the same thing occurs, okay? And then this end of this molecule is attracted to this end of this molecule. That's your IMF. Why is this a dotted line and this a solid line? Yeah.
Because the solid lines are intermolecular and the
Intra. Right. This is an intramolecular. This is an intermolecular. But what does that indicate about its strength?
Intra is so much stronger.
Yes, this is much stronger than this. Okay. So the attraction between those molecules is much less than the bond between these molecules. That's why they tend to draw these with dotted lines and these with complete lines, solid lines. Okay.
So if it has hydrogen bonding, it also has dipole and LDF
Yep.
every time.
Yep, every time. So if you have hydrogen bonding, if you see that that's on there, then you automatically know that it has LDF and it has dipole. So you'd write all three of those down. You have to write all of them down. Yep. Oops, what happened here? Sorry. Okay, yeah, I went to the next page, I think, didn't I?
Wait, so if you have an H bond, you know immediately that it has dipole
Yep.
and
Yep.
So true. Consequences.
Now, why would fluorine be stronger IMF than oxygen or nitrogen?
Because it's more electronegative.
Yes,
More
good.
one-sided.
More electronegative. Excellent. Okay. So here, if we have a nonpolar substance and a nonpolar substance, we're going to have London dispersion forces. That is all that we're going to have, and that would be nonpolar. If we have a polar substance, we're going to have dipole, dipole, and LDF. The strength then will depend on the magnitude and the relative orientations of those molecules. Polar with hydrogen bonding then, it's also going to have dipole, dipole, and LDF. And the strength is typically greater than the dipole, dipole. If it's a nonpolar with a polar, you will end up with dipole-induced dipole and LDF. So the strength of these forces increases with the magnitude of the dipole on this guy.
Okay.
Nonpolar ion, the strength is going to increase as you get larger ions, and smaller ion size will also make it increase and make it more polarizable. And then polar ion tend to be stronger than dipole, dipole. Let me see if I have, just give me 1 second to look at this. Okay, yeah. So this, when we talk about these, this is why primarily, let me go here. This is primarily why, oh, why is this acting funny? Oh, because it's upside down. Like, it's not going the right direction. It's going the opposite direction. I have everything kind of discombobulated from when he was in here. Sorry.
The technician.
Mm-hmm. Mr. Shannon. Okay, so this is typically, when you get a nonpolar and a polar together, this is typically why they don't mix. So for example, if you had oil and water, right? Typically oil and water don't mix. And the reason is because the attraction of those water molecules is so great for one another that they're not going to allow in the oil. Okay? It's not going to split apart and let the oil kind of get mixed in there. And the reason why the oil floats on top is what? It's less dense. Okay? It has to do with density. Okay? So it's less dense. That's why it's on top. But the reason why they don't mix together is because one's polar and one's nonpolar. When you talk about ion or polar and ion, this is why salt water exists. Okay? So when salt goes in, when you put salt in the water, okay, it's going to break up. Actually, I should have that reversed, shouldn't I? Because this would be your ions. So when I put salt in water, what happens is it goes into the water. Do I have like a, let me see if I can pull this up and get a bigger thing to write on, you guys. This is supposed to have some sort of whiteboard or something on it.
Add a slide.
Oh.
I thought I was supposed to have a whiteboard here.
Yeah, I think that's like the main thing. That's my question.
You see what? Oh, here. There we go. Okay,
Yeah.
now I can draw. Maybe it'll let me draw on here.
Oh, no, that would be.
At least it's not a smart board, though. Those things are just
I just need stuff to work once in a while, you guys.
It popped up.
Just once in a while. It wouldn't let me write on it though. Okay. All right. So I've got my sodium chloride. It's sitting in my little cup or whatever. You know, I've got my sodiums. I've got my chlorines. They're here. Okay. Then I put some water there. So I've got my water. Water has a negative end and it has a positive end. And the attraction for this sodium to the water is greater than the attraction between these ions. And that's what pulls the salt apart and gets it into solution. So when I have that, the positive end of the sodium is going to get attracted to the negative end of the water. And it's going to surround this sodium. I'm not working on it. Hold on. Okay. So that surrounds the sodium and it pulls it off. Once that sodium's pulled off, now I've got a chlorine. That chlorine's going to come over here. And how is the water going to be oriented now? Right. The hydrogen end is going to be attracted to the chlorine.
I like that bomb.
It looks like a person who lost his dad.
Yeah, Lippy's never been good at drawing, y'all. You know that.
Listen, you're just like dogs.
Yeah, you like to kill things.
Okay, so that's going to attract. Now, what happens is, just getting out into solutions, which we'll get into in another few days. One of two options, and this is the IMFs that exist between the water. Now, one of two things will happen. Either you run out of these and you have water left over, in which case you have an unsaturated solution, or you run out of water and have this left over. If this is left over, where are you going to find it? At the bottom, because this is more dense than the water. Okay? So if you have some of this left over and not enough water to surround it, then that's called a saturated solution. Okay? So does this make sense? And then these would be ion dipole forces, because you have an ion and you have a dipole.
Oh, dang.
All right, how do I get out of here? There. Okay. Yeah, this never let me write on here. That's why I got rid of that, because it wasn't working for me.
You're like on the finger thing. On the finger, there's like a pen. There's a little fancy pen thing over there.
Oh, the magic wand or something?
That's definitely down there.
Whole class whiteboard.
Yeah.
Yeah.
There you go. There's
You
your
can hit
pencil.
the marker.
Yay.
Oh,
There we go.
dang.
Oh, this is good.
Alright.
I'm glad you're using
That's a lot of steps.
Whew. All right, we figured it out, y'all.
Yeah.
How many of us does it take? We'll figure the thing out.
Just a class.
All right, large biomolecules. What is this guy here? DNA. Very good. Okay. Your DNA is a classic example of hydrogen bonding. That is how the two rungs are held together of your DNA. So you have the one side and you have the other side, guanine and cytosine. Guanine and cytosine, adenine and thymine are held together by 3 hydrogen bonds. Over here, uracil and guanine, and then, yeah, this one is held together by 3. I thought another one was 2. This is, yeah. But I thought uracil was RNA.
Yes,
Yeah, it
is RNA. It is. Because
Why is it connected to
it takes, the U takes place of the thymine.
The T, yeah. So this should be a C. And this is wrong. There's something wrong here. All right. But these are good to see up here. Well, yeah. So you can see these are right. These are fine. This, I think there's some issues down here. All right. So you can see here that your oxygen, and then this is where your hydrogen bond comes in. You've got a nitrogen with a hydrogen attached to it, and it's going to be attracted to the oxygen on this side. Here, nitrogen, hydrogen, it's going to be attracted to the nitrogen over here. here, nitrogen, hydrogen, oxygen over here. And that's how your DNA is structured. It is those hydrogen bonds that hold the two strands of the DNA together. Okay. All right. Not IMFs, but we're going to mention them here. Ionic interactions occur between a metal and a nonmetal. When they lose or gain electrons to form ions, that is your Coulombic attraction or electrostatic attraction. Remember, as the charges increase, that force increases. As the distance increases, what happens to the force? It decreases. Okay. Metallic bonding, we briefly touched on that this year. Metallic bonding occurs between metal atoms. It can be just for one type of metal or a pure substance, or different types of metals and an alloy, which is actually a mixture. Alloys, remember, are mixtures. Metallic attraction then is due to those metallic cations being attracted to delocalized C of electrons. The IMF then is stronger when there are smaller metallic cations. Why would that be? Coulomb's law. All right. And then the last one is covalent network. Covalent network then is between carbon atoms, silicon atoms, carbon and oxygen, or carbon and silicon, or silicon and oxygen. The attraction is due to multiple covalent bonds forming a large macromolecule. The IMF is stronger when there are more covalent bonds. Now, you need to memorize and commit these guys to memory right here. Memorize these.
C dynamine, C graphite, C60, SiO2, SiC, silicon.
What does C16 look like?
I believe that's your buckyballs.
What the heck is a buckyball?
It was actually developed, I believe, up in Madison, which is where they came up with the name.
That would make sense with the name. Just keep that.
Why are you an all cat?
Because my cap lock got stuck on it.
Oh, those things?
Are buckyballs illegal?
Yeah.
Oh, those? I know those. Why are they illegal?
I don't know what they can look at.
I don't know. This is what that looks like.
It's like a ball.
Really, Nicholas?
That's cool.
Not like there's a buckyball.
I like the dynamite shape
Diamond.
more.
But
That's what my,
Yeah, that's it. Carbon 60.
yes, I know it's diamond. That's what my grandfather said. Diamond. He's not very right.
Carolyn Croce.
What?
Using
No.
laser.
I'm wearing a swimsuit. It's kind of hard.
Carbon nano.
I'm wearing a swimsuit too.
You are?
Soccer ball.
Okay.
Dedication.
Let's go with the other ones so they're not big.
I thought there was some link to Madison here, but I don't. I'm not
I think
seeing
it's
it on here.
I think it was higher.
named after Buckminster.
Yeah, that's what it says.
Good for Buckminster.
Yeah. So anyway, that's buckyballs. That is your that's what a that's what C60 is. Okay.
And then, okay, diamond, graphite,
Yep.
C60, SiO2.
Those are the only ones that are carbon network or covalent network that they're going to have on the exam. So if you see those, that should be a red flag to you. If you see like graphite or diamond or silicon something, be very careful.
You just want us to remember that they're
Covalent network, and that is the strongest attraction. That's why diamond doesn't break. That's why they use diamond to like cut other things, because diamond is the strongest natural material in the world. Like we don't have anything stronger. Okay.
So true.
but graphite.
Yeah. And why? Do you guys know why graphite does, but diamond doesn't? Let's pull that picture up.
We watched a video about diamond.
Diamond versus diamond.
All right. So this is why. Graphite is in a two-dimensional plane and it has these different sheets of carbon. Okay. They're attracted a little bit to one another. That's why it holds together. But every time you use your pencil, what you're doing is you're pulling off sheets and layers of this graphite. Okay. With diamond, though, diamond is in a much more structured form here. So you've got a little bit of attraction here, but with the diamond, the structure is much more consistent with, do you see how it's more of a scaffold and how the attractions are? I'm trying to find something in more of a three-dimensional kind of field here. Okay. So because of that, this is very, very strong, whereas your pencil, as you know, you've broken lead before, it's much weaker. Okay. I don't know. Just know that they're.
Okay, good. You guys keep putting it in my mouth.
All right. In general, the properties of IMFs result in the following. Boiling, melting, freezing points are going to increase if you have increased IMFs. That is why, if we go down those halogens, why they continue to get stronger as you move down. Enthalpy of fusion and vaporization. What is this? This is heat. So how much energy do you have to put in to melt something or to boil something? As your IMFs increase, you have to put more energy in to make those phase changes happen. Vapor pressure. We've talked about vapor pressure before. And what vapor pressure is if you have a sealed container and you have a liquid in there, some of that liquid will change to gas. And then there's this constant exchange between these. The lower your IMFs, the more liquid will be found in the gas phase, thus causing more pressure on that container. Viscosity, that's thickness, yeah, like flow. It's resistance to flow, I believe, is what it is. So that, like maple syrup, you can change its viscosity by doing what? Yeah, either cooling it down and making it more viscous or heating it up and making it less viscous. IMFs, as you have more IMFs, the more viscous that material becomes. Why does heating change the viscosity? You are reducing the IMFs as you heat it. Remember, IMFs, you will end up more interference due to that heat energy between those IMFs as you increase the heat. Surface tension, then, that is the tension on the top of a liquid. As we increase IMFs, we increase surface tension. This is what allows bugs to walk across water, for example. You've seen that before, or you've probably tried to float a paper clip on, yeah, we did that as a lab if you had me for chem. You tried to, yep. And then if you have detergents, what detergents do is they interfere with that surface tension and reduce it and allow stuff to kind of mix together that wouldn't otherwise. So that's what a detergent does. It allows the water to mix with stuff that is less polar, like oils, and be able to take them off of your skin. Solubility, then, it depends on the polarity of the solvent and the solute. And that goes back to that drawing that I did. So if you have a, for example, like lead sulfate, okay? If you had this back and forth, this is not soluble in water. And that is because the attractions between these two are greater than the attraction for that lead and the negative end of this water molecule. This is stronger, so it's not going to pull apart. And so that has to do with solubility. Lattice energy then is going to, typically it will increase with increased lattice energy, because the stronger, like for example, if you have this guy versus this guy, the lattice energy here is going to be greater than here, okay, because this has a bigger charge than this does. All right, let's look at the next, the I do's here. Identify the type of intermolecular force present in each of these. We have pentane and we have octane. Both are hydrocarbons. Which one is going to have a strong, what is the IMFs involved here? These are just a series of carbon, hydrogen. It's just going to go like this until it gets to the end, and then repeat that. So what IMF is present here? LDF, that's it. Yep, that's all we have. Which one is going to have a higher vapor pressure? Why? Right, there's less electrons. This is less polarizable. So that's going to lead, if we had two containers that are sealed with both of these in there, okay, this one has less LDF, so more of that's going to be in the gas phase up here than this guy. Okay, if this is octane. So this is going to exert less pressure than this. Does that make sense? All right, boiling point of HF is 293, whereas the boiling point of F2 is 85 Kelvin. Determine the types of intermolecular forces present. So HF, what is its intermolecular forces?
And dipole. Yes.
Okay, and what about F2? LDF. Okay, now this has a lower boiling point than this guy. Why? Lower IMFs equal a lower boiling point.
Okay. Good.
So for homework tonight, you got the UDO, which is, looks like 8 problems.
Can I see my test? Me too, Evie. Just study during lunch. Or are you going out with dudes?
Katerina, I paid mine and I emailed you the receipt.
Yeah. What? I know, I'm just scared if it's optimization. I don't remember optimization.
It's from you to you? Okay.
I remember, I don't have to do it.
I'm working on it. Don't know.
What?
It so much.
No, it's not. That's unit 2.
Well,
I like watching the World Cup.
Is that yours?
I don't understand. Me neither.
All right, Brie, I fixed it.
One time I was at a softball. He was here for the
Can I come in at 6:45 tomorrow for directions?
Yeah, that should work.
Thank you.
Well, and you may have to email me because I don't know how early she gets in.
Okay, so
So
have you opened the door?
if she can't, yeah, if she can't get, like, if she's not there, like, you know, if you press the button and nobody answers, email me and I'll come up and get you. I will try, yeah, go. I will try, Matthew, to get here at 6:45. I will do my best. I maybe, that's about the time I get here. So, and I come in these doors over here and I have a gray pickup truck. So if you don't see that gray pickup truck, it'll be the only one probably parked out here that I'm not here yet.
On Wednesday, we're just doing notes. I won't be here for the first part.
I don't know. You'd have to look on your schedule. I don't remember what we're doing. Just come around the other side and unplug it.
Oh, you can see it. There you go.
Push it towards the cabinet so nobody trips over it. Just kick it with your foot. Okay.
Nicola, do you want it?
What? Sure.
You.
I was too lazy to look for it.
There's a test. Yes. On the thing on the back, it should
Oh, I
say
want to
that.
look at mine.
Maybe you can convince DC no test.
And you're lying, there's no test.
She told us that Friday.
No, she didn't.
Yes, she did.
There's no test. If anybody else said there's a test.
Just lined up by my door. I don't like that.
Where did I get a -1 on this? I labeled all the things.
I gotta go too long.
I labeled all the issues.
No, I'm not even says.
But they're SP2, SP3, SP. They're, yeah, I don't know what the hell.
I told her that, so I
I don't have any
know.
numbers on them.
She's nuts.
Some of them are twos.
You can do, are you gonna go ask her? I know.
That's a
Well,
good point.
BB's class is doing it tomorrow. Which we were behind BB, so I don't know why.
We're doing it before that.
No, Monday. Last Monday. Where I gotta sleep at 9.
Get away from my door! I don't want that. I want this.
Dude.
You're making me grumpy.
I think you're still recording.
Dude.
Yep, you're right.